Download this code from codegive.com, link in the description below. LTO fatal error, bytecode stream generated with LTO version, a deep dive and practical guide. Link time optimization, LTO, is a powerful compiler optimization technique that performs global analysis and transformation across the entire program during the linking stage. While it can significantly improve performance, it can also be a source of frustrating errors, especially when dealing with different versions of LTO bytecode. One common error you might encounter is the bytecode stream generated with LTO version x.x not compatible with LTO version y.y, where x.x and crying face are different versions of LTO. This detailed tutorial will cover the following. 1. Understanding LTO and its role. What is LTO, and how does it differ from traditional compile time optimization? 2. Causes of the LTO version mismatch error. Why does this error happen? What are the common scenarios? 3. Diagnosing the problem. How can you pinpoint the source of the LTO version incompatibility? Compiler flags, build systems, and library versions. 4. Solutions and best practices. Rebuilding everything with a consistent compiler. The most reliable, but potentially time-consuming, solution. Using appropriate compiler and linker flags. Specifically, how to influence LTO versions. Managing library dependencies. Ensuring library versions are compatible with your compiler's LTO. Conditional compilation. A less desirable, but sometimes necessary, workaround for specific libraries. 5. Example code and demonstrations. Practical examples that show how the error manifests and how to fix it. 6. Troubleshooting tips. Additional strategies for identifying and resolving this error. 7. Preventing the issue in the first place. Best practices for maintaining a consistent build environment. 1. Understanding LTO and its role. Traditional compilation and optimization. In a standard compilation process, source code files, .c, .cpp, are compiled into object files, .o, independently. The compiler optimizes each file in isolation. The linker then combines these object files into an executable or library. Optimizations are limited to the scope of each individual compilation unit. Link time optimization, LTO. LTO, also known as whole program optimization, WPO, changes this process. Instead of emitting native object code, .o files, the compiler emits an intermediate representation, often called bytecode or bitcode. This representation is similar to the LLVMIR. During the linking stage, the linker collects all these bytecode files and combines them into a single unit. The optimizer can then analyze and optimize the entire program as a whole, including functions that are called across different source files. This enables optimizations that are impossible in traditional compilation, such as inlining. The compiler can inline functions from one file into another, even if they are in different libraries. Dead code elimination. Unused functions and variables can be removed, even if they're only unused due to cross-file relationships. Global register allocation. Registers can be allocated across the entire program, potentially reducing memory accesses. Interprocedural optimization. The compiler can optimize function calls based on information about how the functions are used across the whole program. Benefits of LTO. Improved performance, smaller code size, faster execution. Reduced binary size. Better code quality due to global analysis. Asterisk drawbacks of LTO asterisk. Asterisk slower build times, the linker has more work to do. Asterisk increased memory usage during linking. Asterisk potential for linker errors, especially version mismatches. 2. Causes of the LTO version mismatch error. The bytecode stream generated with LTO version x.x not compatible with LTO version. Crying face error indicates that you are trying to link object files, or archive files, i.e., libraries, that were generated with different versions of the LTO intermediate representation. This usually happens when inconsistent compiler versions you are using different versions of the compiler, example GCC or Clang, to compile different parts of your project or its dependencies. Each compiler version might use a slightly different LTO bitcode format. Mixing pre-built libraries with custom compilation. You are linking against pre-built libraries, example system libraries or third-party libraries, that were compiled with a different compiler version, an LTO version, than your own code. Partially rebuilt project. You rebuilt some parts of your project with a new compiler version but didn't rebuild all dependencies or the entire project. This can leave some object files with an older LTO version. Build system issues. Your build system, example Make, CMake, Ninja, Auto Tools, might not be correctly configured to handle LTO, leading to inconsistencies in how object files are compiled and linked. 3. Diagnosing the problem. Here's how to investigate the cause of the error. Examine the error message. The error message itself is a clue. It tells you the two incompatible LTO versions that are involved. Identify the involved files. The linker error message should specify the object files or archive files, .a or .so, that are causing the problem. Note their paths. Compiler version check. GCC use GCC version to determine the version of GCC you are using. Clang use Clang version to determine the version of Clang you are using. Compare the compiler versions used to build your project and its dependencies. Object file inspection, using LLVM objdump. The LLVM objdump utility, part of the LLVM tool chain, can be used to examine object files and determine if they contain LTO bitcode. It can also tell you the version of the bitcode. Example. This command searches for the .llvmbc section, where LTO bitcode is typically stored, in my_object_file.o and then greps for the string LTO version. If the file contains LTO bitcode, the output will show the LTO version. If the file doesn't contain LTO bitcode, then it was likely not compiled with LTO enabled. This can be a useful clue. Build system configuration. Inspect your build system's configuration files, example makefile, cmakelist.txt, to ensure that LTO is enabled consistently for all parts of your project and that the compiler flags are correct. Library dependencies. Check the versions of your library dependencies. If you are using pre-built libraries, make sure they are compatible with your compiler version and LTO settings. You might need to rebuild these libraries from source using your current compiler. Verbose build output. Add the v, verbose, flag to your compiler and linker commands. This will print out the exact commands being executed, including the compiler flags and linker options. This can help you identify inconsistencies. 4. Solutions and best practices. Here are the most common and effective solutions. Rebuild everything with a consistent compiler. This is the most reliable solution. Ensure that you use the same compiler version, including minor versions and patch levels, to compile all parts of your project, including any dependencies you build from source. This eliminates the possibility of LTO version mismatches. This may be time-consuming, especially for large projects with many dependencies, but it guarantees compatibility. Remove build artifacts, object files, libraries, before rebuilding to ensure a clean slate. A typical approach is: then, reconfigure and rebuild your project. Using appropriate compiler and linker flags. Enabling LTO. Use the floato flag during both compilation and linking. For example, specifying LTO level. Optional, you can control the level of LTO optimization using floato equals x, where x is a number, example floato equals 1, floato equals 2. Higher levels generally provide more aggressive optimization, but can also increase build times. The default is typically equivalent to floato equals 1. If you're targeting maximum performance, experiment with different levels. Thin LTO, Clang/LLVM. For large projects, consider using thin LTO, which is a faster and more scalable form of LTO. It involves a lightweight analysis phase before the full LTO optimization. Enable it with floato equals thin. Gold linker. Using the gold linker, especially with GCC, can significantly improve LTO linking performance, especially for large projects. To use gold, pass fuse LD equals gold to the linker. You may need to install the binutils gold package on your system. Managing library dependencies. Pre-built libraries. If you are using pre-built libraries, make sure they were built with a compatible compiler version and LTO settings. The easiest approach is often to avoid pre-built libraries that you're not 100% sure about. Rebuild from source. Ideally, build your dependencies from source using the same compiler and LTO settings as your main project. This ensures compatibility. Tools like VCPKG, Conan, and SPAC can help manage dependencies and build them from source. Package managers. Use package managers, like apt-get, yum, brew, chocolatey, to install libraries, as they often ensure compatibility within the system. Static versus dynamic linking. Static linking, embedding the library code directly into your executable, can sometimes avoid LTO version issues because the library code becomes part of your main project's LTO process. However, static linking can increase the size of your executable. Use the static flag during linking to perform static linking. Note that it's not always possible to statically link everything, licensing issues or dependencies might prevent it. Conditional compilation, use with caution. As a last resort, you can use conditional compilation to disable LTO for specific parts of your code or for specific libraries. This involves using preprocessor directives, if-def, if-and-def, to exclude certain code sections when LTO is enabled. Example important notes. Conditional compilation should be used sparingly. It reduces the benefits of LTO and can make your code more complex. It's often better to try other solutions first, such as rebuilding libraries with a consistent compiler. Make sure your conditional compilation logic is robust and doesn't introduce new bugs. 5. Example code and demonstrations. Let's create a simple example to demonstrate the LTO version mismatch error and how to fix it. Scenario *. We have two C++ files, main.cpp and libcpp, and we compile them with different GCC versions. Then, we try to link them together with LTO enabled. Steps to reproduce the error asterisk. 1. Compile libcpp with GCC 9, or older. 2. Compile main.cpp with GCC 12, or newer. 3. Link with GCC 12 asterisk. You will likely encounter an error similar to fixing the error asterisk. The simplest solution is to compile both libcpp and main.cpp with the same compiler version, example GCC 12. This will resolve the LTO version mismatch error. Example using cmake asterisk. This cmake configuration enables LTO globally, make _enter procedural _optimization true. Critically, it explicitly finds a C++ compiler and sets cmake_cxx_compiler to ensure that cmake uses the same compiler for all compilation tasks. 6. Troubleshooting tips. Clean build always start with a clean build, remove all object files and intermediate files, before attempting to rebuild with LTO. Compiler driver be consistent in using the same compiler driver, example GCC, G++, Clang, Clang++, throughout your build process. Debug information consider adding G to your compilation flags to include debug information. This can make it easier to debug issues, even if they are related to LTO. Reduce test case if you can't easily identify the source of the problem, try creating a minimal test case that reproduces the error. This will help you isolate the issue. Experiment with LTO levels try different LTO levels, example floato equals 1, floato equals 2, floato equals thin, to see if one level works better than others. Floato equals thin might offer a good balance of performance and build time. Check system libraries ensure that your system libraries are compatible with your compiler version. Sometimes, older system libraries can cause issues with LTO. You might need to update your system or use a different distribution. Static linking of incompatible dependency if the error mentions a dependency and is consistently problematic, try linking it statically, using static for that specific dependency to integrate it fully into the LTO process of your main executable. Note that legal/licensing factors may make this impossible. 7. Preventing the issue in the first place. Consistent compiler version The most important preventative measure is to use a consistent compiler version throughout your entire project, including all dependencies. This means carefully managing your build environment and ensuring that all developers on your team are using the same compiler. Build system configuration configure your build system, example cmake, make, auto tools, to enforce the use of a specific compiler version and LTO settings. Use environment variables or configuration files to control these settings. For example, in a make file, you might define dependency management use a robust dependency management system, example vcpkg, Conan, SPAC, to manage your project's dependencies. These tools can help you build dependencies from source using your current compiler, ensuring compatibility. Continuous integration, CI use a CI system to automatically build and test your project whenever changes are made. CI can help you catch LTO version mismatches early in the development process. Configure your CI system to use a consistent compiler version. Containerization, Docker, etc. Containerization can provide a consistent and isolated build environment, ensuring that all developers are using the same compiler version and dependencies. Define your build environment in a Docker file and use Docker Compose to manage your build process. In summary asterisk. The LTO fatal error, bytecode stream generated with LTO version error is a common issue when working with LTO. By understanding the causes of the error, using the proper diagnostic techniques, and following the solutions and best practices outlined in this tutorial, you can effectively troubleshoot and prevent this problem, enabling you to reap the performance benefits of LTO without the frustration of version mismatches. Remember that the key to a successful LTO experience is consistency in your build environment and careful management of your project's dependencies.